calculus lesson on the chain rule. Alright guys, there is a warm-up, so make sure, just take a look at it. We'll be doing it in class, but it's always a good idea to take a look at it, and if you have no idea what to do, then it's a good idea for you to go back and look at the previous notes, because every warm-up problem is basically a review question, okay? So it's built-in review every day, alright guys? Do you ask for extra problems? Here it is, right? Alright guys, let's get started with the actual lesson itself. So we will talk about this one more time. So what's going on? What is that equal to? Okay. So you could view this in a couple of different ways, right? You could think of it as a product rule. If you look at it as a product rule, let's say is equal to sine of x times x, right? Like this. Then we know that the u is equal to v, and the u prime, which is v prime, is equal to cosine of x. So f prime of x is uv prime plus vu prime. And that gives you, what is this? Look at that. So u is equal to sine of x. The v prime is cosine of x. And the v is sine of x. And that is cosine of x. And this is equal to twice the sine of x, cosine of x, right? It's not the most important thing at this point, but you should know your trig properties and realize that is a sine of 2x using the double angle formula, right? Now, maybe some of you guys thought that, hey, wait a minute, that looks like a power rule, doesn't it? And you're thinking, so if that's the case, you're like, wait a minute, an f prime of x is twice the sine of x. But that result is different. These two are not the same. So which is right? Okay, let's do just quick graphs to see what happens. Okay, so normally sine of x sort of looks like this, doesn't it? Yeah. All right, there you go. And that is 2 pi, and that is pi. That's 1 and negative 1. But if I'm drawing a, let's say, I don't know, square of that, 1 squared is 1, negative 1 squared is 1. And the value here that was a half becomes a quarter right here. So it looks more like this, doesn't it? So that is the graph of sine x squared. Why don't we take a wild guess and check? Okay. At, let's see, pi over 2. What happens? What is the slope at pi over 2? Hold on. So pi over 2 over here, of this, it should be 0. So that you could tell from the graph, right? So f prime of pi over 2 should be 0 from observation. And that's what happens in the first method and the second method over here, right? In the first method, when you do plug it in for pi over 2, I get twice the sine pi over 2 cosine of pi over 2. But that's 0, isn't it? And that's 1. That's the whole thing is 0. How about the second one? If I plug it into that one, what I end up with is twice the sine pi over 2. That's 1. So the answer is 2. Clearly, that's not the case, right? So this is wrong. All right. What happened? All right. Well, that is because the power rule applies if that's x. It applies to monomials, not if this thing is a function. So what we have over here is a composition of functions. Okay. So that's a problem. So what do I do? Okay. All right, guys. Actually, before we continue, though, the warm-up for this one, right? may be a good idea, okay, because this will actually help you, right? So why don't we just do this part, right? Just do this part, because I was gonna hold it to the class, but I think it's kind of important. So yeah, these are compositional functions, and your job is to find the f of x, g of x, and h of x. I want you to break this down into at least 2 or more, right? So f of x is the outermost, and followed by the g of x in the middle, h of x, and so on and so forth. So every function over here, y of x, is written as f of g of h of x. Okay? And why don't you define the f, g, and h for me? Okay, guys? I want you to go ahead and pause the video. Alright, guys, thanks for pausing the video, and I appreciate you letting me sort of interrupt the overall flow. Yeah, I was gonna wait, but I figured, you know what? Let's just do this part. We could just do this part, the second part, in class. Okay? There it is. So if you did it as a 2, that's what it is. But let's go by layer, outside in. It's a something to the 5th, outside, and then 3 times something minus 5, which is 3x minus 5, and the last one is a squared value. Okay? You want to go outside in. So the outermost thing, so this is when you do by 2, but you know you could break this down, right? So when you do this, it's like e to the something. That something is outside, and what is that something? It's a sine of 2x. But you know that this could be broken down into sine of something, and that something happens to be 2x. Using similar kind of ideas, yeah, so this is like 1 over something, that's x, and that something happens to be cube root of something minus 1, right? And that something happens to be x cubed. You could even break this up into more, actually, because you could have said x, and you could have said x minus 1, and then that x was cubic, right? So it all depends, but I wanted you to break it down to 3's in this one, right? And we have one over here. All right, so this will require a little bit of room, so I think you could sort of start here, but you may have to continue on the back side. Okay, guys? All right, let's get back to where we were. The reason why we need to sort of get back to where we are is that we needed to recognize, right? Because I didn't want to spoil it, right? Like I didn't want to give you a hint that this is a compositional function, right? So now that the cat's out of the bag, let's talk about it, okay? So when you have a compositional function, right, you may have something that looks like this. We may have f of x, capital F of x, could be defined as small f of x, g of x, like this. That right there is the outer function, or outmost function, and that is the inner function. Well, that's all very nice if you only have 2. But if you had 3 like the previous one, the y of x, let's say, is small f, g, and h of x, let's say, right? And this is the outermost. This is the middle. And this is the inner, right? But if there's more than 3, instead of saying the middle, I might say second outermost, the third outermost, and the whatever's in the right and smack in the middle, we'll call that inner, right? Okay. So once we break it down, the chain rule goes something like this. So this is your chain rule, obviously. We're implying that is used for composite functions. So in this particular case, df dx, right, is equal to df, capital F, we do the derivative with respect to the outermost, right? In this case, that'll be d small f, and then you do d small f, right, with respect to the g, right? And then we do g with respect to x. So we're using Leibniz's expression, and if you look carefully, right, the f's cancel, dg's cancel, we'll be left with df dx. We're done. That's right, guys. Yeah, that literally is it. Okay? But if we're using the prime notation, right, f prime of x is f prime of x. Actually, why don't we just keep everything as it is? Just leave it blank. So whatever it's in here, we're going to carry it, which we'll fill in a little later. And then we're going to pull that out like a Russian doll almost. And we're going to do the derivative of that, right? Which will be g prime of x like this. Okie dokie. All right. Actually, I made a little boo-boo. All right. So we're expressing this over here. So what I should have said, I misspoke completely. I don't even know why I did that. So this becomes like df dx, right? So this is equal to this way. Sorry about that. Okay. I was thinking about something else because what I was thinking, in fact, was the next example that I was going to show you, right? Sometimes, I tell myself this, I tell you guys, but I need to practice myself, is I need to focus on the now, and sometimes I think too far ahead and just babble as I just do the current work. My apologies. What if you have 3? What do? So what if the f is equal to f of g of h of x? So df dx is essentially the derivative of the outside, inner, and the middle, right? Let's write that with the Leibniz's notation first. That would be df dg. So this is what I was thinking about earlier, right? And then we do dg dh, and then we go dh dx, right? If I can pull that out a little bit. So basically, we're looking for df dx is equal to, okay? So normally this is the way we write it over here, guys. We're just saying that this compositional function is the big F, and we're expressing it this way, okay? All right. So that's how we would arrive at that. So if you think about this, the dg's cancel, dh's cancel, we're left with d small f dx, and that's what we have. Now, some people like doing it this way. In fact, I learned to do it this way from Dr. Raj, my calculus teacher in high school. But I know there are a lot of places where they prefer the prime notation. They're big fans of Newton, I guess, right here. No, the real reason is that it's simpler, it's quicker, it's more efficient, right? This makes more sense, though, if you think about it, okay? So now what do? So what we do is big F prime is we do the outside first, big F, small f prime, and then we pull out whatever's inside, pull it out, and that would be this, wouldn't it? So that's g prime of whatever. And whatever's inside, we pull it out. We do the derivative again, and that would be the h prime of x. Now, why don't we do one more, Mr. Yim? Well, we do. When you take the x out and do the derivative with respect to x, d dx of x is 1. Dot, oopsie, times 1. So that's why we don't write it, right? Now I'm going to go back and backfill this everything. So what was inside of the f? This. I just copy everything as it was. And then g, everything inside as it is. So it's like a Russian doll, You open the f, and then you pull it out, and you open that up. So f prime, you could think of it as opening it up. And then whatever's inside, boom, we open it up. X, there's nothing more to open. That's it. We're done. Right? So there it is, guys. That's what we're doing. Okie dokie. So let's go back and look at this. So if we're looking at this, what we actually have, right, is that this is equal to maybe u of x squared, right? Let's look at it a couple different ways, right? We already had the answer, right? Which was the answer was, from previously, we knew that the answer was 2 sine x cosine of x, which we could write as sine of 2x like this. All right? So when you're doing this using the Leibniz's notation, df dx is equal to df du times du dx. Well, df du, if you sort of think about this, this is like a u squared, isn't it? If you're doing the derivative f with respect to u, that's just 2u. And du dx, where you take the derivative of that, which is sine right here, right? So we could say that the u of x is sine of x, and du dx is equal to cosine of x, and it will be cosine of x. We substitute everything in there. U is equal to sine of x, cosine of x, which is equal to 2 sine of 2x. Oopsie, no, sine of 2x. Sorry about that, guys. There you go. We got the same result. That is one way of doing it. The second way is, as we talked about earlier, the f prime of x is the derivative of the outside, which is the u prime of x, right? So the easy way to write that for us would be to, what is the derivative of something squared? That would be twice that something. And then we're going to pull that out, take the derivative of that, d dx of the sine of x. And that gives you twice the sine of x, cosine of x, which is twice the, oopsie, no, making the same mistake, sine of 2x. Hey, you're looking at this like, some of you, I know some of you are thinking this because I get this question every year. So again, why do we do this? Why can't we just multiply things out? It'd be so much easier. Well, yeah, maybe. But what if I ask you to do something with the 12th power? What are you going to do then? You're going to do sine of x, 12 copies of that, and just group them that way? How long is that going to take? Right? So because we know the chain rule, this is a more robust way of doing it, right? So the f prime of x, therefore, is the u squared, right? U of x squared. To the 12th power, that is. When you take the derivative of the outer function, that gives you 12 times the u of 11 times, that's not a double prime, that's u to the 11th power. So maybe I should do this. U of x to the 11th power plus the u times u prime of x, right? And that will give you 12, and the u of x is what? Sine of x? Sine of 11 to the x times u prime is cosine. And we are done. It is that quick, guys, right? So the length that it takes you to do using chain rule of the sine of x to the 12th power is about the same as sine of x to the 2nd power. Because like in terms of its structure, it's like the same thing, right? So what I'm trying to do is, there's a second set of ideas we're learning today, which is to find the derivative of the exponents, right? Exponential functions, right? So if you have the derivative of a, here's a constant, obviously, a to the x, the formula for that is a to the x times ln of a. What that implies, so this is a more general case, right? Because we learned that d dx of e to the x, if you follow the same rule, would have been e to the x times ln of e, but that's 1. That's why the derivative of e to the x was e to the x. Now the difficulty comes in when instead of having an x over here, let's say you have a function. What do? Well, that's basically as it is, times the ln of a, times the derivative of that. So that is the, how do you apply the chain rule for this? So how do I do this one? Okay. So f prime of theta, copied as it is, cosecant theta over 2, times the ln of the base, which is 4. These, I want you to try these 4 problems first. Okay, pause the video, guys. Okay, good. So I'm going to walk you through the rest. The key to doing this is that it's a power over here, guys. Express that as square. Yeah? And then that becomes u squared, gives you 2u times the derivative of the du dx. And I did that separately over here, which comes out to 3. And then we substitute back the u and we're done. And same thing with the next one, right? I write that as, ooh, I made a boo-boo. Yes, I did. Because it's in the denominator, it's actually negative. Yeah, do you see that? Yeah. So that should have been 1/3. Yeah, it's negative, and that should have been 4/3. Oh, silly me, right? And then multiply by the whatever's inside with the derivative of that, which happens to be 2x plus 1. So let me fix this a little bit. So that should be 4/3, like this, and that should be 4/3. Okay. Yeah. So you might want to double check. I mean, like me, when you're rushing through stuff like that, you might make mistakes. So you always want to double check, triple check. Is the exponent, should that be positive, should be negative? Because that is 1/3, because it's in the denominator, that should have been a negative, right? Good. The next question, very similar, once again, as what we did earlier, ln of 2, so copy as it is, ln of the base times the derivative of that, which happens to be 5. So I did that separately and write it out. We're good. In this case, that was just prime number, so we don't have to worry about it. If it's a number to the power, the great thing about log property is you can bring it to the front and simplify the expression that way. Last but not least, ooh, yeah, it's UV. So we did the product rule. So first one derivative and second one derivative, that requires you to do the chain rule. Yeah? The derivative of the cosine is negative of the whatever, and then you do the derivative inside. That whatever is inside. Okay, not that it's not important. So negative and negative makes it positive. Here we go. And because it is overall a product rule, I just plug and chug. So the calculus portion of this was from here to here. That was it. The rest is algebra. And that's the way it is for throughout the rest of the calculus class. Alright guys, so once I plugged it in, that's what I got. I kind of did this. I didn't factor out 6x because I didn't think it's going to look any better. So I just left it as it is. Alright guys. Alright, so that is it. The rest of the problems over here, we'll be doing that in class because it's your turn. But as usual, you should look at them. But leave some for the class so that you could talk to your classmates and bounce ideas and stuff like that. Just below that, we do have challenge problems. I did put an answer there for you as an extra practice beyond the practice. Alright guys, that is it for me. Have a good night.